So what is, so every time when I have a differential equation which is first order, I will first look whether is it linear or not. Because that's the reason I was in the first lecture explaining you linearity. So seeing a differential equation, you have to determine whether it's a linear or not. If it is linear, you will convert in this form right away. You will just express that differential equation in this form. You will figure out what is your px, what is your qx, and then you start solving a problem. So this is first two steps. Now this is a differential equation right here. What makes you think this is linear? There is no powers of y. There is no multiplication of y prime with y. There is no x function being multiplied with again powers of y, or there is no tan y or cotangent y or secant y or these kind of function, exponential of y. So this is a linear, a nice linear problem, first order. So here my px, as I can see, this is already in the standard form, is -1, and qx is -2 e to the power x. This form is called as standard form. Yes.
So if something's being multiplied by the y prime, we should divide by that problem?
If something is being multiplied with y prime, we have to divide it.
3x y prime minus y equals -2x. And the x we divide by 3.
We have to divide by 3x. That's right. We have to divide by 3x. And then it will be 1 over 3x will be px. Right. If there is something with this y prime, we have to push it here, because as you can see in this form, there is nothing with y prime. Right. So we have to always convert in this standard form. Okay. So in this differential equation, my px is what?
E to the x.
Everybody agrees?
Yes.
Okay, good. And qx is again e to the x. Okay, so now how will I solve this? So tell me first thing here, let's try to solve this differential equation, the second one. It's more trickier than the first. Okay. Is it separable? Can you separate it? I want an answer from everyone. You have to try it. See, can you write as fx dx gy? If you can, then we don't have to invoke a new method. We can just do it by that.
What do you mean? F of x is e to the x, and then g of y is negative y plus 1.
Very good. That's right. It is separable, and you will pull out e to the power x in this, and you will get negative y plus 1. So this function will represent your gx, and this will represent your fy. And if you try to solve this by separable, you can very quickly just go ahead and do separate the variables, right? Right? So exponential is not at all a problem, as we can take it out in both the terms. And then I will get minus ln of 1 minus y e to the power integration is e to the power x plus a constant of integration. Now, in this equation, are these the only solution? Did I capture all the solution of this differential equation? Did I miss something? What did I miss?
You forgot to check where g of c equals 0.
Right, and what is g of, well, now, since my notation kind of, so as per the previous representation, this is f and this is g. So you have to check g of this function is 0 because now this is the denominator, right? So what is the, anything which we are pushing to the denominator basically. Doesn't matter how you name them, but anything which we are pushing to denominator. So y equals to 1 is a solution which I missed. So is y equals to 1 a solution of this differential equation? Let's check it. When y is 1, the right hand side is 0 and derivative of 1 is 0. So it is a solution which we didn't capture here, right? So y equals to 1 is a singular solution. And this is a general basically family of solution. So all together they become a family of solution. This and this, everything all together, because all of them are solution. But we are just being very careful in the ones which we are missing. What actually is happening at this y equals to 1, if you geometrically try to see in a differential equation, what is y prime at y equals to 1? Y prime is 0, right? So the value at which derivative is 0 means what? Derivative 0 means what? Constant, right? So y equals to 1 is a constant solution of this problem. So if I give initial condition anywhere in that whole line, so basically if I start anywhere, let me put it here only. If my initial condition is x equals to 0, y is 1. So if I say in this differential equation, let me not write in this graph, but let me write it separately down here. I'll underline this, and then y prime is minus e to the x y, and I'll write a different and a new problem here. This is a problem which is same as before, but I have inserted extra condition, which is y0 is 1 with this differential equation. Now, is it an initial value problem? Is it an initial value problem? First order differential equation, one initial condition, IVP. Okay, so if this is IVP, you are expecting what out of it? A unique solution, right? So now geometrically if I try to see, at 1 the derivative is 0, so that means solution has to be constant. So I do not have to go forward and solve this problem. The solution will remain 1 forever. Solution is just 1 for this problem. The reason is solutions are unique, and if for initial value problem, and if I have started at 1 here, and I know at y equals to 1 derivative is 0, so that means if I start at here, I will stay here. Okay, so this will remain the solution of the differential equation. I do not have to further solve it. Solution trajectories, although there are so many solution trajectories, as you can see with C, solution will change for a problem. But what is interesting about these solutions of differential equation is they will never cross each other. They will enjoy by themselves, but they will not interfere with any other solution. Something like that. So if there are nice trajectories of solution, they are going, but they will never even cross, and they will never even touch each other, which you cannot see through the numerical schemes when you are trying to computationally find the solution. And the reason they don't touch and cross, because if that happens, what will be a problem? If they touch or they cross each other, then if suppose they are crossing each other, then this is a marker. It will exploit this idea of uniqueness of a solution. So if I have two solution curves like this and they are crossing at this point, say, if they are crossing at this point, then what is happening? I can pick this as an initial condition. And if I pick this as an initial condition, then the problem is, do I go like this? Do I go like this? Which direction? Suppose this is a backward trajectory of a solution in the backward time, and this is in the forward time, but still it creates a conflict. Which solution should I pick? So uniqueness gets exploited. It will no longer be a unique solution. So that's the reason they will never cross, because we want them. We want solutions to be unique, and we place the the coefficients to be continuous to achieve that thing. If the coefficients are not continuous, IVP might not have a unique solution. If the coefficients Px and Qx are not continuous, it's possible. Okay, so that's also a very important point. The coefficients has to be continuous. Okay, now coming back to this type of problem. So as you all mentioned just now to me, this was separable and I don't even have to learn any new method. Let me then pick this one and try to work it out, this problem, this example. So now, is it separable? First order, is it separable? What do you guys think? So suppose what you try to do is you will maybe first try to push this y on the right? And then now it's an addition, so how will I write as a product of the functions? I cannot. So this is not separable. So separable method cannot be used here. So I have to figure out something else. Okay? So this is not separable. Differential equation. Okay. Is it linear? Yes. Can I make it separable? Now that's the next question. You will say, well, we already have said it's not separable. Why she's asking, can we make it separable? But yes. Yes. Multiply by y coefficient. Right. That's the idea. I really want to combine these left hand side two terms into some different function which will make this differential equation separable. So can I make it separable? And answer is yes. So how? I will compute. So this is now I am not okay, so I will compute what? Find a function ux which is e to the power integral px dx. Okay, so what is that function here in this scenario? E to the power minus x. I will not put a constant of integration here. I'll just cook this function. Now multiply this function throughout the differential equation. So what we will get? We will get e to the power minus x y prime minus e to the power minus x y equals to minus 2 e to the power x times e to the power minus x. I will come to the real justification in very shortly, but first I want to demonstrate through an example so that you get it when I will be speaking. So I just multiplied, I'll come to the point. E to the power minus x in this whole, what are you noticing on the left? Is it d by dx of what? E to the negative x y. Let's see product rule. Y prime e to the negative x. E to the negative x derivative is negative e to the negative x times y. So by product rule, this left hand side get merged into the function which I computed times the unknown function y. And this is going to happen every single time. This is the power of, this is the real power of this function. And this will be your and the mathematical name for this will be integrating factor. So once you able to find this guy, you just multiply this guy in the entire differential equation, and what he does is he combines the left hand side two terms into itself times the unknown function derivative. That's what this common friend is doing. This common friend, when gets multiplied in the entire differential equation, when it starts playing its role, then it somehow combines itself with the unknown function derivative and merge the left hand side two terms. And the right hand side is e to the power x minus x is e to the power 0, which is 1. So it's negative 2. Okay? Is it clear to everyone? Because this equation was already in the standard form. So I compared this equation with my previous standard form which I mentioned, pxy equals to qx. That's a good question. So that's how I got px to be negative 1. That's a good question. I was thinking about this equation in the standard form. And then that's how I got minus 1. And once I have this nice thing right here, how will I get a solution? Integrate both the sides. There you go. You get e to the power negative xy is equals to negative 2x plus a constant of integration. Add a constant first before pushing this term on the right. So y turns out to be minus 2x e to the x plus c e to the x. Yes, you have a question?
Yeah, so the reason we didn't put the c on when we integrated the integrating factor is because it would combine with the c again. Is this why?
Right, it will eventually combine. So just ignore it in the integrating factor, the constant, and just put the constant right up here. Okay, so this is how the first order linear differential equations are all about. what you do eventually is, I can illustrate how this thing even come into picture, and that is the derivation which I have on the next couple of slides.
So we have this right there that you like underlining is that after you multiply everything by the negative x, you simplify it to d over dx the negative x y equals 0.
Right.
So in between those two steps, like, how do you guys
Okay, so this step is clear, this one first. This step is, you have a differential equation right up here. What I did is, in this differential equation, I multiplied this guy throughout. E to the power minus x throughout. Once I did that, then I start observing my left hand side. Left hand side eventually turns out to be the guy which you multiplied times the unknown function. And this happens every time. Whatever is that integrating factor is, times that y will be your always the outcome up here. And you can check it right now in this particular problem. E to the power negative x and derivative of y, product rule. E to the power negative x derivative is negative e to the power negative x times y. Right? So this is exactly these two terms. The left hand side gets always combined. This is a real magic which happens, and it just happens. It just combines these two terms and make it a separable differential equation, which you can integrate both the sides and solve for y. That's it. So any first order linear differential equation, you first convert into a standard form, find the px, find this integrating factor, multiply it throughout the equation, combine the left hand side two terms, integrate both the sides. That's the whole scheme for linear first order differential equation. Is it clear to everyone? We will do a couple of more examples in the next class, and then I'll move on to more explanation.